Good evening. Welcome to the second of our briefings tonight at the Space Telescope Science Institute in Baltimore. We have tonight with us Dr. Heidi Hammel, who will be discussing in just a moment the first image from the Hubble Space Telescope that we received just a short while ago this evening. Dr. Hammel?
Thank you, Doran. I just want to get it right over with and show you this image. If we can have the image, please. What you're seeing is a full disk of Jupiter taken with the wide field camera in a blue filter. The wavelength is 410 nanometers. And you see on the left a blow-up of the impact site. It's expanded and enhanced so you can see it. It's very dark. We have wavelengths ranging from 3,036 nanometers out to 956 nanometers. We don't have those all ready to show you now because we obviously haven't had enough time to do that. But I'd like to describe for you what it looks like. At all wavelengths except a methane band, it looks like this. It's dark, and it has this dark material to the south. In the methane band image, the wavelength is 889 nanometers. Everything that you see as dark there is bright. It's completely inverted. Looks like a negative image. We don't fully understand what we're seeing here yet. We don't have ready for you yet images that were taken in the previous orbit. In that orbit, what we could see at all wavelengths was what looked like a plume on the limb of the planet, and then we saw the plume flatten as if it was spreading out, and that was all we saw. We detected it at all those wavelengths, though. And so we'll be working throughout the night to get these data ready to show to you tomorrow morning. I would now like to show you a video. If any of you are not convinced that this is from this comet, I would like to show you a video of what Jupiter looked like yesterday. And this is brand new preliminary data, and it's in a fairly raw format, so you'll see seams and colors that if we had had more than 18 hours, we would have done a prettier job. But I wanted you to see the quality of imaging that we're getting from the Hubble Space Telescope. So if we could run that video, please. It was created by Eric DeYoung based on 6 orbits of data yesterday afternoon. And I hope we have the video.
Can you roll the video, please? Okay, it's going out on the satellite. We'll have it here shortly.
Okay. This will basically take 5 different images of Hubble, and what we have done is map project them and then recombine them to make basically a sphere. I hope we do get to see it. Well, while they're working on that, let me just show you the geometry of this impact in case some of you are a little bit confused, because that's a very confusing image. If this is Jupiter and you're all on the Earth, you're looking this way, okay? Jupiter's spinning like this, okay? These impacts, this train of comets, nuclei, are coming in from the bottom at about an angle something like this. And you can't see them happen. All right? There we go. Let's take a quick look at the video. This is a very rough reconstruction, but you can see the amazing quality of the images from the wide field camera. And there is the site. It's going to stop on the right longitude so you can see the pre-impact view. There's the great red spot and a white oval. This is the wide field camera. With the planetary camera, we're going to get even better resolution. And we'll, of course, we'll have a little bit of time to clean this up, and it'll be a really nice video when we get that chance. Okay, that's the view, very similar, not quite exactly the same, but similar to the impact site. You see the great red spot, and you see that little white plume off to the side, just below and to the left. And if we could go back to the other one, I don't know if that's possible or not. Yes, we can. We'll look again for the great red spot and that white spot, and you'll see where the little black thing is next to it, the impact site. Well, we're going back. A little bit of dead time. Okay, in the meantime, while they're working on that, continue my story here. All right. You could not see the impacts occurring, although the Galileo spacecraft, you'll all remember, is in a perfect view to get some good pictures of that. And so that will be fascinating to see. Here we go. See the great red spot? See the little white oval? And now further on you see that black splotch. It was not there the day before. It's a new feature on Jupiter. And we're going to have 20 more of them. Even brighter. It's going to be a great week. So I think I'll stop there and let the rest of my team have some time to talk.
Okay, I'd like to go ahead and introduce the other members of the science team. Thank you, Dr. Hamill. To her left, Dr. Hal Weaver of the Space Telescope Science Institute, member of the Wide Field and Planetary Camera 2 and Faint Object Spectrograph teams. Next, Dr. Keith Knoll of the Institute, a member of the Faint Object Spectrograph and High Resolution Spectrograph team. Next is Dr. John Clark, University of Michigan, and a member of the Wide Field Planetary Camera 2 and Faint Object Camera teams. Following that is Dr. Bob West of Jet Propulsion Laboratory, and he's a member of the Wide Field Planetary Camera. And at the end, hi down there, Dr. Melissa McGrath of Space Telescope Science Institute, a member of the Faint Object Spectrograph and High Resolution Spectrograph teams. And what I'd like to do at this point is turn it over to Hal and just for a few brief comments and the discussion members of the team, and we'll open it to Q&A.
Okay. First of all, I'd just like to say it looks like this comet was not a dud. Let it ring out to the rest of the world. We've had a wonderful time observing this fascinating object up until now, but of course it's been highly uncertain as to how big these pieces are. We took just some images of the comet on Thursday, and there were some reports that the comet was fragmenting, but in fact, when you look at the Hubble images, there was no evidence that the pieces were fragmenting. And the fact that we see a plume coming out of this explosion is very strong evidence that these nuclei are traveling very deep into Jupiter's atmosphere. It's hard to understand how you have something that's going to shoot out above the limb by 1,000 kilometers or more unless you had a plume formed, an explosion deep down in the atmosphere. That would be my preliminary guess of what's going on.
All right, just for a couple of moments, I know everyone is prepared here for a lot of questions, and we would like to go ahead and open it up in just a moment. But we do have right now to show you a video that was taken just a few minutes, actually a few hours ago during the initial receipt of the data here at the Hubble Institute. So go ahead and roll the video, and we'll see the reaction.
So it's on the way on the other side. Okay, we're looking for something. Why don't you go back?
This is the first one.
Yeah, this is the latitude that we're looking for something right there. The contours you could tell pretty well, but there wasn't too much there.
We will rerun this.
So there's a red spot, so you know. Atlas is yeah, that's it.
My God.
That's it.
Okay, we'll rerun this in here.
Look at it. Look at 953. Wow. This is not even gotta get the internet.
Yes.
To do it.
For the benefit of the members in the gallery here, we will have a rerun of this tape later. We apologize, we had some tape sync problems. The signal went out on the satellite okay, however I understand, so we will replay it, and we have some dubs available for the media that need that after the briefing. I apologize for that, but we're all working in real time here, and we do have a few difficulties with some technical equipment as we're trying to work through. But I'd like to open it up to questions and answers if we're all ready for that here in the Institute in Baltimore. And please wait for the microphone and state your name and affiliation. Any questions? In the front row. Wait for the microphone.
Linda Howe, Chancellor Communications, Philadelphia. In one of the email releases out here, it said that the Nordic Optical Telescope in La Palma in the Canary Islands had reported that 2 hours after the first bright image was seen, that a black dot became visible in the video image of Jupiter at exactly the same position of this bright impact. What could make this black dot be seen 2 hours after this impact we're looking at here?
All right, I think it's pretty simple. Part of the answer to that is pretty simple. The impact occurred at a certain time, and we saw apparently a plume on the limb of Jupiter at that time. And then as Jupiter rotated rotated around as it does, the impact site came into our view, and that impact site is a place where we now see dark material. And so as Jupiter continues to rotate, that's coming more and more into our field of view. And I think the fact that they're reporting seeing that 2 hours after the initial plume is that initially it was close to the edge of where the sunlight is and very difficult to see on the edge of Jupiter. And I think their camera system was probably not good enough, didn't have enough resolution to see that until it rotated far enough into view that they could pick it up, whereas we saw it essentially immediately, or at least in the next orbit. And there's also the question that maybe part of your question is, why are we seeing black material? And that's a more interesting question. I don't think anybody expected us to see black material. I certainly didn't. I expected that we would see perhaps bright material in the methane image, which we do see. But in other images, I thought we might not see anything. And I'm going to speculate now about why we might be seeing black material. There's a couple of possibilities, and I think what we're seeing here are particles either from the comet itself or particles that may have been dredged up from deeper in Jupiter's atmosphere. If the particles are from the comet, they could be partly silicate particles and maybe a little bit of iron in there. They could also be carbonaceous material, which normally is black. The trouble with that explanation, though, is that we expect that material to have undergone very high temperatures, something like 40,000 degrees Kelvin. At those temperatures, any particles would vaporize. The carbon would probably go into carbon monoxide gas, and we wouldn't see it. That's one reason it's very puzzling. As the fireball would rise out of the atmosphere, the plume rises, everything cools very quickly, and out of that cooling cloud you expect things to condense, like silicates and maybe even some of these carbonaceous particles if they're still around. And finally ices, like water or ammonia ice, we expect would condense as the thing cools enough. Now ices we expect to be white. So again, we're puzzled. Why are we seeing dark stuff? And going further in speculation, we expect that in Jupiter's atmosphere there's a lot of sulfur, although we haven't observed it spectroscopically yet. We think there is. We think that if there's material dredged up from the atmosphere, it might be rich in sulfur as well as other things, water and ammonia. Sulfur can form colored compounds, and just what kind of compounds would form in this situation I'm not prepared to say. And so I'm guessing that maybe sulfur ions in some form are contributing to this dark stuff.
Just a quick follow-up. In addition to the mystery of the color, I also wondered if seeing this 2 hours after perhaps the initial impact, does that mean that we could be seeing the residue of these impacts for much longer than anyone ever thought?
I'm not sure about longer than anyone ever thought, because in my thinking, I expect that we should be able to see the residuals, these particles in the stratosphere, for possibly a year or longer. And in fact, when I proposed to do this observing, it was to look over long time scales to use these particles as tracers of the stratospheric motion. I see this, I viewed this event as possibly analogous to on Earth when there's a large eruption from like El Chichon or Pinatubo. Volcanic eruptions put particles high in the atmosphere where the stability of the atmosphere is very stable, and therefore particles can reside there for a long time. And in fact, on the Earth, this is one way we learn about the dynamics and circulation of the stratosphere is by watching how these particles spread with time. And so I saw this as the first opportunity ever of doing this kind of thing on Jupiter. And the timescales for spreading on Earth in the stratosphere are of the order of a year or so. And I expect that we may still be seeing stuff a year from now from these events.
Right here at second row. Wait for the mic, please. And also, I'd like to ask the panel members to introduce yourself also to help us out here. Thank you.
Bob Cook, Newsday. I understand one of the really interesting possibilities was that comets might get deep enough to punch through the water clouds if they exist. Do you think that might have happened?
One of the, Keith Knoll from Space Telescope Science Institute. One of the key things in all the spectroscopic observations that we'll be looking for, both with Hubble Space Telescope and ground-based telescopes, are molecules that are dredged up from the deep atmosphere. And as you said, the water cloud would be one of the things that we'd be looking for very keenly. The reason for that is that if we see a huge increase in the amount of water, more than could have come from the comet itself, we'll know something about the energy of the impactor and how deep it penetrated into the atmosphere. So we'll be using these molecular clues, the debris from the comet and the stuff churned up from the atmosphere, to tell us things about the size of the comet, how deeply it penetrated into the atmosphere, and as Bob alluded to before, possibly allow us to see molecules that until now have been too deep in Jupiter's atmosphere for us to sense remotely.
In the past few weeks, we've been told that amateur astronomers have little chance of seeing this event. Does what you've seen so far make you a little more optimistic about what the unwashed masses or the semi-washed masses, might see?
I'm Melissa McGrath from the Space Telescope Science Institute. The most dramatic results we've seen so far, brightness-wise, have actually been in the infrared. And so unless they had infrared instruments, I think actually in the visible it's unlikely that this would have been seen. Hubble saw it because it has such good resolution. And when you see the images tomorrow of the first plume that we detected, it was very small, and very close to the limb. And because Jupiter's so bright, that's very difficult to see with anything but Hubble. So I imagine, we know that the B impact is at 10:30, and some of us would actually like to go outside with our binoculars at 10:30 and look, because B is a lot bigger than A, and so, or a lot brighter than A, so we think that means a lot bigger. So, you know, it wasn't so bright in A in the visible, but B may be brighter, and I think we should all go look.
Here at the second row front. And please state your name and affiliation.
Glenda Chu, San Jose Mercury News. I'm a little puzzled about how to describe this thing to readers. Was it dark, was it bright, or what? Because some of the email messages were describing something bright enough at certain wavelengths of light that it outshone anything else on Jupiter, from the things that look like polar caps in the methane band to anything else, and even outshone Io. And then you're talking about, I guess, in the visible wavelengths, the thing is dark. And so I don't know, if I tell people that this is a real bright thing and it outshone everything, am I really misleading them? And what is the significance of this methane band or the infrared bands that you're observing? What are you seeing that is different from what you're seeing in visible light?
Okay, I'll take that. I'm John Clark, University of Michigan. Let me start with the infrared bands. In the infrared, you can think of it as heat. As much as it is light. As you go farther into the infrared, you're sampling lower temperatures. And these were at temperatures that are much hotter than what we have here in this room. They were at wavelengths of about 2 microns, where it appeared very bright. And there it appeared bright because that one localized region was much hotter than the tops of Jupiter's clouds overall. so it appeared to have a high contrast. When we look at these visible wavelengths, we're looking at sunlight that's reflected from the cloud tops. And there's relatively less contrast here than you see in the infrared, but there's more information about the disturbance because we have the better resolution. In the methane band filter in particular, we're looking at a particular wavelength of light, of sunlight, that is absorbed by gas, methane gas, in Jupiter's atmosphere. And there, Jupiter overall appears much darker because the sunlight is being absorbed by the gas that's normally in the atmosphere. And there, the comet fragment appears relatively bright, just as a matter of contrast. So it's a relative brightness thing there. We also will be getting images in the ultraviolet wavelengths. The first ones come in well, about 8 or 10 hours will be taken, and they'll come down tomorrow. And in the ultraviolet, which is my main interest, we'll be observing the very highest parts of Jupiter's atmosphere. And from what we've seen already in the lower parts, I'm looking forward to seeing the images. And we'll get those tomorrow about noon.
Up in the front.
Bill Harwood, CBS, and I might have missed this earlier, and if I did, I apologize. Can anyone give us a scale for the structure that we're seeing here?
That box.
And the timing of it, how long after the impact this was, and how big this is? And I have a follow-up.
The box that you see, the zoom box, is about 2 Earth diameters. So that structure that you're seeing, that circular pattern, is about the size of the Earth. Jupiter's a big planet. Remember that this is the A impact. G is much brighter.
I am remembering that. My next question. Actually, a whole bunch of questions, but I don't suppose that looking at this raw data that we know or have any better guesstimate as to how deep this thing plunged. I mean,
Well, as I said, the fact that you see the plume means that, you probably went very deep and produced a fireball like the theorists have been describing. And, we have a plume that extends out more than 1,000 kilometers above the normal limb of the planet. So I think that's pretty good evidence that, these impacts really are 200,000 megatons of TNT or more.
I guess what I meant was, does this match what you would expect from the model, how deep you thought you would get to get this kind of effect?
There were so many models, you could have matched anything.
Unveiled by the Shoemakers earlier tonight. I mean, is this matching pretty much what they were expecting?
We missed the press conference.
We were watching the images come in.
We can tell you that when the Shoemakers saw the images, Gene Shoemaker was extremely happy, so.
Apparently it matched pretty well.
And the last question for me is, how surprised were you people are really?
Did you? Well, you couldn't see that video, but we were pretty darn surprised. This is in my dreams, the kind of stuff we saw.
We couldn't have gotten any better.
No, this was incredible.
Next question, second row.
Ron Cowan, Science News. So is there an agreement now about when A actually hit Jupiter, or hit?
We're working on that right now.
And would you say Hubble saw this a minute after, a few minutes after, 30 minutes after?
A few minutes. A few
hour and
minutes.
a half. Well, that is, but we saw the image on the limb, and that was probably within 10 minutes?
Yeah.
5 minutes.
A few minutes.
5 to 10 minutes, yeah. And some of the ones later on in the week are actually impacting closer to the limb, and they are brighter than this.
I would say one thing, the G probably has an energy that's about 25 times as high as A.
I'm just checking in. That black spot there is the diameter of Earth? Is that what you're saying?
Well, the box, you can fit 2 Earth diameters in that box.
What about the black spot, which is the...
That would be half the Earth diameter, maybe, but that's what everybody agrees with that, yeah. Third to a half.
And lastly, again, at the moment, what's the best estimate for the diameter of fragment A?
Between 1 and 2 kilometers.
Hi, I'm Noel McCormick with Space Times. Is there, they took the image off, would acoustic energy be visible from these strikes?
Well, Mark Marley would think so.
We have a lot of debate about that.
And possibly the dark area away from the, that surrounds this, the darkest area, could that be that type of energy?
We've been debating it.
My preference is to say no. I think it's very difficult to make something dark on Jupiter from a pressure wave of something like that. I think the likelihood is that anything that's dark on Jupiter is caused by particles in the atmosphere that are absorbing light. But as I say, this is far from being settled, and I think time will tell.
We also have a better data set than this to look for those kind of phenomena. And furthermore, those phenomena are most likely to be detected in infrared imaging, because those waves are temperature changes. And so that's the primary way to detect them. We're here seeing sort of a secondary effect from the temperature change. So it will be very interesting to see what the infrared telescopes around the world see from those brighter impacts.
Next. Down here.
Jim Reston for Esquire. Does this first image give us any insight into the question of whether there'll be a permanent cyclone on Jupiter?
It's too soon to tell.
Yeah, and when will we start to get some fix on that question?
Months? No, days? Days. Andy Ingersoll from Caltech says days.
Okay, we're going to go to a center right now for a question. Not sure which one we're lined up first. Perhaps they're not on the line right at the moment. We'll take another one here in this room. Down front.
Question will be, my name is Shin Yoshikawa, NHK. I think this question will be Dr. McGrath. Do you see some change at the plasma torus or the aurora at Jupiter in this stage?
Actually, we don't do observations with the Hubble Space Telescope of the torus until the end of the week. We will do some observations with the IUE satellite on Tuesday, I believe it is, of the Io torus. One interesting thing that was reported closely related to that is that some Japanese observers, radio observers, apparently saw a tenfold increase in the decametric radio emission from Jupiter well before the impact. So there is some evidence that there was a large disturbance in the magnetosphere. So I think we have high hopes that there may also be disturbance to the Io torus. There haven't been any auroral images with HST since the impact, but there will be, and we should be able to answer that question soon.
Those first auroral images will come down tomorrow.
We're going to go to Kennedy Space Center now for a question there, and we'll come back after that. Go ahead. State your name and affiliation, please.
This is Joe Chen, Earth News. Can you establish a minimum mass now for this piece, and assuming the rough density that you've been assuming, just how much kinetic energy was involved in it? Can you establish any lower limit now that would have been required to produce the effect that you saw?
I think the fact that we see the plume and apparently some very hot stuff, which seems to back up some of the models, or some of the models predicted this kind of phenomena if the impactor was about 1 kilometer in size. The fact that we see something close to that indicates to me that we're talking about something roughly 1 kilometer in size, which means roughly 200,000 megatons of equivalent TNT. But whether or not it's 1 kilometer versus 2 kilometer versus even 500 meters, I think that I couldn't say that right now. I couldn't tell you which one versus the other at this point.
Follow up, please.
For either member of the spectrograph teams, were you able to do any quick spectrograph of the area, or is that still in the future? And what would you expect at 889 nanometers at the methane line?
The first spectra, we've gotten baseline spectra over the last few days, but the first spectra we're going to get will be of the G impact site, and that's going to be on Monday morning. All our spectra are going to be ultraviolet spectra. Visible wavelength spectra will be done from ground-based telescopes, and infrared spectra will be taken also from ground-based telescopes. So we are doing what Hubble can uniquely do, and that is obtain high-resolution ultraviolet spectra.
And what can you tell us, anybody in the panel, about these other images? I realize that you're just showing us the blue one, whereas you took several different snapshots in different wavelengths as far as just how different do they appear, and will you get us either a false color or an imitation full color picture by the morning?
Well, I'd like to get a little sleep tonight. At most of the wavelengths that we looked at, the feature appears to very similar to what we're showing in the blue. So at almost all the wavelengths, this dark streak with that circular pattern around it is what you see. The only exception is the methane band wavelength. And as I said before, that appears to be a complete negative. What you see dark is bright. So you see a little bright streak with a little bright swirl around the bottom of it. It's too soon to talk about colors of this thing yet because we just simply have not had the time to work on it. We will probably be trying to put together some color reconstructions. I can't guarantee that will be tomorrow morning. We'll do the best we can.
I'd like to come back to the Telescope Institute here for some more questions in front.
Tagi Amirani, BBC Television. It's quite clear that the science team is very excited about this, and you guys are going to have a lot of data to go through for months to come. But what's in it for the guy on the street? What does it mean to him?
He can be glad he doesn't live on Jupiter. Well, you mean in terms of the knowledge? We've never had the opportunity to know in advance that a comet or a broken up asteroid or whatever it is was going to hit a planet. This is the first time in the history of humans we've been able to look at this and study it. And we're lucky now that it's a big one so we can really see the effects. And we'll be learning more about how that process operates and how deep these effects are in the atmosphere of Jupiter and how long they last. This has relevance to the Earth, we think, more in terms of the origins of the Earth. We believe that the Earth was formed by accretion of material coming in from space, and this gives us an idea. There's been talk about whether this might have been caused the demise of the dinosaurs. We won't probably be able to prove that, but we'll learn more about the general process and the history of the Earth, and maybe the future. So.
Can I just add to that? I think there's a little bit more to it than just the science. And of course we're interested in the science here because that's what we do. But it's a fascinating thing. I mean, there are things whizzing around the solar system, smashing into other things with huge explosions. And that's just really incredible to think about. I mean, you know, we don't often think about the universe out there. We just sort of look at the sky and the stars are there, big deal. But if we really take a step back, and it's a really dynamic world out there. It's a dynamic universe. And this is just a key example of some of the energetics that go on.
Next question, second row.
From the estimate of the size of the plume, do we have any fix on whether enough material will be deposited around to create a new ring around Jupiter?
Well, I think that, you know, all of that material is just going to fall right back down. The stuff that might contribute to the ring is the stuff that misses Jupiter. Basically, you know, the dust that you saw around the comet, you know, everything that, you know, you saw in that plume is coming right back down. You know, it's gravitationally bound to Jupiter and is, you know, not going to escape. So we do have, you know, we had a fair amount of dust, and maybe there will be people looking for the formation of a ring.
Front row.
Is there anything about any of your
please wait for the mic. And
is there anything about any of your experimentation that might indicate when this is all over whether there's any kind of a more solid core in the center of this otherwise gaseous planet?
I'll answer that, I guess. We already know a lot about Jupiter, and from Voyager flybys and Pioneer spacecraft flybys, we have a pretty good idea of its interior structure. And we know that there is a probably a solid core, but that is very much deeper down than these comets could possibly penetrate. The only thing that, well, there is another piece to this. The seismic wave phenomena may end up telling us something about something different, and that is the boundary between gaseous hydrogen and a phase of hydrogen that comes about only under very high pressures and in Jupiter. We believe that this occurs, although it's not exactly clear where that transition occurs. So there's some hope that we'll learn about that.
Just a quick follow-up. Is it possible that any of these pieces could penetrate deeply enough into wherever this hard matter is that part of the dark stuff actually could be substance from the hard interior of Jupiter?
No.
Any further questions? Oh, front row.
What do you expect from the larger impacts down the line with what you know now?
More spots.
Yeah, this is just a preview. It looks like it's going to be an even bigger show for the rest of the week.
The only thing special about this one was that it was the first one. And we've got some 20-odd more to go, including some much brighter ones.
So you would expect the bigger ones to penetrate farther, perhaps?
Sure.
Next over here. Please, name and affiliation, please.
Chris Leach from NHK. Is there anything you can tell about what kinds of chemical reactions were taking place during the impact?
Should I start?
Yeah.
Not from this. This is just strictly imaging, but now I'll pass it over to Keith.
Yeah, that's what we hope to learn about later in the week when we get the spectroscopic data back. That will tell us about the composition of the atmosphere.
Okay, if there are no further questions, I think we will go ahead and wrap it up. And what we'd like to do before we close and lose the satellite is have another replay of the still image, and we'll run both the videos. And for the benefit of those here, we'll have that on the monitor. Also, I want to remind everyone that tomorrow morning, Sunday morning at 10 a.m. Eastern Time, we will have a briefing which will have more images, also some information from other observatories in the NASA and NSF observing campaign. And at that panel, we'll have Doctors Shoemaker and Carolyn Shoemaker and Dave Levy, and member of the Hubble science team. And we hope to see you out there, and that will be also live on NASA Select with Q&A from the centers. At that point, we'll go ahead and close the press conference. Thank you for coming, and we'll see you tomorrow morning. Thank you.
These spots are bright.
So it's way on the other side. Okay, we're looking for something. Why don't you go back?
This is the first orbit.
Yeah, this is the latitude that we're looking for something right there. Contours you could tell pretty well that there wasn't too much there. This is the 4-second thing.
So there's a red spot, so you know. Atlas
Oh, wow.
Yeah, that's it.
Oh, my God.
That's it.
Look at that.
Spread out.
Look at
You can see it every
Look at 953. Wow.
Unbelievable.
Gotta get to the internet.
Just try to do it.